Having seen universal quantifiers and logical expressions involving quantifiers and the operators such as and or, let's look at existential quantifier with operator or now. Subsequently, we'll look at and. So we wish to know whether this is same as this. Let's attempt a proof. From this, I perform existential instantiation so that it becomes P of A or Q of A for some A. Okay, and note that the expression P of A or Q of A is true for some A. So this one is true. So it may be the case that P of A is true and this one is false, or this one is false, this one is true, or both are true. Okay. We don't know. We only know that P of A or Q of A is true for some A. For that A, if you look at the truth value of P of A, this could be true, this could be false, or it could be false, true, or both are true. Okay, so this is what we have. Now I'll rewrite this as P of A for some A or Q of A for some A. But when we write like this, you have to be careful. Over here, it is the A is same. But when you bring the statement for some A separately for this, the A in this may refer a different A. The A that is referred here may be different from the A that is referred here. Whereas over here, for the entire expression, it is some A. So the A that is used here and that is used here, it is one and the same. But if we rewrite like this, then this A is different from this A. Okay. It may be same, or there is a possibility that the A that is referred here and the A that is referred here, maybe they both are different. Okay, so this one cannot rewrite like this. Okay, this is not possible always. So what we will do is, let's look at case. Case is P of A is true. Okay. If P of A is true, P of A for some A. Fine. Now from this you perform existential generalization. You get there exists X P of X. Fine. Now I am slightly modifying this. P of A for some A. So P of A for some A. With that, I am adding one more statement, Q of A for some A. Okay. So with respect to this some A, it is true because we are in this case. With respect to that A, Q of A may be true or may be false, but we need not worry because this one is R. So A referred context is same. So what we refer here and what we refer here is one and the same. Okay. Now I can perform generalization and write this as there exists x p of x, or there exists x q of x. We know this one is true because this one is true, so this one is true, so this one is true. Because this one is true, the entire expression is true. This may be true or this may be false, which we need not bother at all. So this being true implies that this being true. So one has to be careful. One cannot write this always. However, if you are in the case where p of a is true, you need not bother about what this value is. Whether for that sum a, q of a is true or false, we need not bother, because this one is true. Because this one is true, this one is true. Therefore, this implies. You can run a similar case analysis assuming q of a is true. So q of a is true, so you get there exists x q of x. With that, you add p of a, and subsequently you generalize that. So because this being true, you see that the entire expression is true. Therefore, there exists x p of x or q of x implies there exists x or there exists q of x. Please note, if you look at our argument, from this we get this, it is by definition, and from this we run case analysis, either p of a is true or q of a is true, and each of them is equivalent to this statement. Therefore, the biconditional is true. Biconditional is true always with respect to the operator R. Fine. Let's look at the related expression. There exists x p of x and q of x. Does this imply there exists x p of x and there exists x q of x? Let's attempt this. So when we perform existential instantiation, this becomes p of a and q of a for some a. Remember, if this is true for some a, then it must be the case that p of a is true and q of a is true. Correct? And so this implies that p of a is true for some a, q of a is true for some a. I can do existential generalization and say there exists x p of x and there exists x q of x. So this being true, meaning p of a and q of a is true for some a, it means this must be true and this must be true because this is AND. Now perform existential generalization, we get there exists x p of x and there exists x q of x. Fine. So this implies this, and from this we conclude this. Therefore, we get to see that there exists x p of x and q of x implies there exists x, p of x, and there exists x, q of x. Now what about the converse? So does this imply this? Answer is no. This does not imply this. Why? You may see this, right? This one is true with respect to, say, the first element. Say x is equal to x1. And say this one is true with respect to, say, second element. Because it only says there exists x. So the x that is referred here and x that is referred here is, they are different. Now this is true with respect to x1, this is true with respect to x2, therefore the entire expression is true. However, you come here, when you look at this, and with respect to x1, if you see that it need not be true. With respect to x2, if you see, it need not be true. Over here, x that is used for p and x that is used for q are different. Over here, I should use the same x to talk about the truth value of p of x and q of x. Okay, let's investigate that part. Okay, whereas for this one it was true, as you can see here. So we proved this part. Look at the converse of this. There exists x p of x, or there exists x q of x. Now this one is true. Let's assume this one is true, which means p of a for some a. Now this implies that p of a or q of a. You can add another proposition, still this is true, because this one is true, the entire thing is still true, independent of what q of a returns. Whether it returns 0 or 1, it is, or true or false, this one is still true. This implies existential generalization. There exists x, p of x or q of x. Similar argument for this. If this one is true, then q of a is true for some a, then this implies that q of a or p of a, from this we get this. Okay, so which is why we said this one is bi-equivalent, whereas this one we doubt, because this may be true with respect to variable x1, this may be true with respect to x2. Over there, because the operator was or, we had that advantage. Independent of what q takes, this one was true. But over here, that's not the case. We are concerned about the truth value of this as well to conclude this expression. But interestingly, from this discussion itself, we see that this direction is false. We can establish a counterexample. Let us consider this. Let's assume UOD has two elements, x1, x2. We build counterexample from this itself. So predicate P is such that P of x1 is true and P of x2 is false. The predicate Q is such that Q of x1 is false and Q of x2 is true. Now look at the statement, there exists x p of x, there exists x p of x, so this is true. There exists x q of x, this is also true. With respect to x2 it is true. With respect to x1 this is true. Now what is the truth value of there exists x, p of x and q of x? Suppose x takes the value, there exists x, let's assume x takes the value x1, then p of x1 and q of x1. P of x1 is true and q of x1 is false, so this one is false. Suppose x takes the value x2, then p of x2 and q of x2, one is true, the other one is false, so this is also false, which means there is no x for which this one is true. So this is true, this one is false. Here is a counter example. So how do we establish a counter example? When you have expression x implies y and intuitively you think x does not imply y, then you look for a counter example such that it is true for the expression x and false for the expression y. Here is one UOD and appropriate values with respect to the predicates p and q. You see that the left expression is true, which is x in our case, whereas the conclusion is false, or premise is true and conclusion is false. And this is the standard trick. Fine. So with respect to R, it is biconditional, both directions are true. With respect to AND, one direction is true, the other direction is false. And similarly for universal quantifier as well, we saw that with respect to AND it was true, biconditional. With respect to OR operator, only one direction was true, whereas the other direction was false. Now one can bring other operators. I can ask for is this true? There exists x, p of x implies q of x. Does this imply there exists x, p of x implies there exists x, q of x? So just like we brought in logical operators OR and AND with respect to quantifiers, one can bring other logical operators and study the truth value, and does this imply this, or is the converse true, all that. One can also ask for expressions involving both. Something like there exists x p of x implies for all x q of x. Is this same as saying there exists x, p of x implies q of x? So for all this, what do? We look at this, then apply universal instantiation or universal existential instantiation, simplify and see whether conclusion follows. And in the process, you may have to simplify using well-known identities and equivalences.